If an interviewer asks what are Spark optimization techniques, a weak answer is to randomly say, cache the data, increase executor memory, use broadcast join, and increase the cluster size. Those are individual techniques, but that is not a structured answer. A strong answer is to divide Spark performance optimization into 4 areas. First, reduce the amount of data Spark reads. Second, reduce expensive data movement and shuffle. Third, manage partitions and output files correctly. And fourth, avoid unnecessary computation. So in this video, I am going to explain the most important Spark performance optimization techniques in that exact order. By the end, you will have a structured answer you can use in interviews and a checklist you can apply to real Spark jobs. Hello everyone, welcome to BigData Fact. I am Pranit and I have 4+ years of experience working as a data engineer. And if this is your first time visiting this channel, don't forget to subscribe for more content on big data and real world insights. Here is the structure for today's video. Let's start with the first goal, reducing how much data Spark needs to read. Part 1, read less data. The first technique is filtering data as early as possible. Imagine a table contains 5 years of historical data, but your report needs only the last 30 days. There is no reason to carry 5 years of data through joins, aggregations, and transformations and then filter it at the end. Apply the filter close to the source. This reduces the number of rows that participate in the rest of the execution. However, filtering is most effective when the storage layout and data source allows Spark to skip unnecessary data. That brings us to predicate pushdown. Predicate pushdown means Spark pushes the filtering condition down to the data source. Instead of reading all the data into Spark and filtering it afterward, the data source attempts to return only the data that matches the condition. If predicate pushdown is supported, the Parquet reader can use file metadata to skip rows that cannot contain India. This reduces disk input-output and the amount of data entering Spark. One important thing, filtering early and predicate pushdown are related, but they are not exactly the same. Filtering early means placing the filter before expensive transformations. Predicate pushdown means the filter is executed as close to the source scan as the connector supports. The next technique is column pruning. Avoid reading every column when the transformation needs only the few columns. Do not read unnecessarily and continue carrying 100 columns through the complete pipeline. Instead, select only the required columns. Reading required columns reduces disk input-output operations, memory usage, serialization, network transfer, and shuffle size. The next technique is use columnar file formats. Predicate pushdown and column pruning work especially well with columnar formats such as Parquet and ORC. In row-oriented text formats such as CSV, Spark may need to read and parse complete rows even when only a few columns are required. Columnar formats store values by column. That means Spark can often read only the columns needed by the query. They also support compression, schema information, column statistics, and efficient analytical scans. So for repeated analytical processing, Parquet or ORC is generally a better choice than repeatedly processing CSV or JSON files. So far, we have reduced the data entering into Spark using early filtering, predicate pushdown, column pruning, and columnar formats. Once less data enters the job, the next major performance problem is usually data movement. In Spark, moving data between executors is called shuffle, and joins, aggregations, repartitioning, and sorting can create expensive shuffles. The part 2 is reduce shuffle and handle skew. When joining a very large table with a small table, Spark may be able to use a broadcast join. With a broadcast join, Spark sends the small table to each executor. The large table does not need to be fully shuffled by the join key, but do not blindly broadcast every dimension table. The broadcast dataset must fit safely in executor memory. If it is too large, broadcasting it can cause memory pressure, timeouts, or executor failures. Check the table size and inspect the execution plan before forcing a broadcast. The next technique is use AQE and handle data skew. AQE stands for Adaptive Query Execution. Normally, Spark creates an execution plan before the query runs, but the optimizer does not always know the exact size and distribution of the data in advance. AQE uses runtime statistics to adjust the plan while the query is executing. It can coalesce small post-shuffle partitions, change certain join strategies based on the actual table size, and split skewed shuffle partitions. Data skew happens when one partition receives much more data than the others. For example, imagine 199 tasks finish in 30 seconds, but one task takes 15 minutes. The entire stage waits for that slow task. AQE can automatically handle some skewed short-made joints by splitting oversized partitions. For severe or unsupported skew patterns, we use salting. Salting means adding an additional temporary value to a heavily repeated join key. For example, a customer ID is 100, can temporarily become 100 underscore 0, 100 underscore 1, like that. This spreads the records across multiple partitions. The corresponding rows on the other side of the join must also be prepared to match those salting keys. Salting is useful, but it adds complexity. So first, inspect the distribution, enable or verify AQE, and use manual salting when automatic skew handling is not enough. Now the part 3, manage partitions and output files. First, understand Coalesce versus Repartition. Coalesce and Repartition both change the number of partitions, but they are not interchangeable. Repartition performs a shuffle. It can increase or decrease the number of partitions or redistribute the data more evenly. Use repartition when you need more partitions, you need to redistribute uneven data, or you want data partition by a specific column before a large operations or write. Coalesce is mainly used to reduce the number of partitions. It usually avoids a full shuffle by combining existing partitions. That makes it cheaper, but the resulting partitions may not be evenly balanced. So remember, repartition is shuffle plus better redistribution, can increase or decrease partitions. Coalesce usually avoids full shuffle, primarily reduces partitions. And be careful with Coalesce of 1 on a large dataset. It can force the final processing or write through very limited parallelism and become a bottleneck. The next one is fixing the small files problem. Too many small output files create another common Spark performance issue. For example, imagine a table contains 200 gigabytes of data, but it's spread across 50,000 tiny files. Opening, listing, tracking, and scheduling work for thousands of files creates overhead. Future Spark jobs may spend significant time preparing and opening files before meaningful process even begins. Small files are often caused by too many output partitions, high cardinality partition columns, frequent microbatch writes, or writing without controlling the final partition count. The possible solutions include using Coalesce or repartition before writing, choosing a sensible partition strategy, compacting small files after ingestion, and using AQE or rebalance capabilities where appropriate. And do not solve small files by always writing one giant file. The goal is not the minimum number of files. The goal is reasonably sized files with enough parallelism for downstream reads. At this point, we covered reading less data, reduce join shuffle, handling skew, managing partitions, and controlling small files. The final category is avoiding unnecessary or inefficient computation. First thing here is cache versus persist. Caching can improve performance when the same expensive data frame is reused multiple times. Without caching, Spark may recompute the full lineage for every action. Cache stores the result using Spark's default storage level. Persist gives you more control over the storage level. Depending on the storage level, data can be kept in memory, on disk, serialized, or replicated, but cache only when the data frame is reused. Caching a data frame used only once wastes memory and can increase garbage collection or cause useful data to be evicted. And when the cache records is no longer useful, call unpersist. The final technique is avoiding Python's UDF when Spark already provides you built-in functions. For example, instead of using a Python UDF to classify revenue, use Spark built-in functions. Built-in Spark SQL and data frame functions are visible to Spark's optimizer and can participate more efficiently in query planning. Traditional Python UDFs may introduce serialization and Python execution overhead. So if an interviewer asks, what Spark optimization techniques do you know? I would answer like this. First, reduce the amount of data Spark reads by filtering early. Use predicate pushdown, selecting only required columns, and using columnar formats such as Parquet or ORC. Second, reduce shuffle by choosing the correct join strategy, broadcasting genuinely small tables, enabling or verifying AQE, and handling skew using automatic skew optimization or salting. Third, manage partitions correctly by understanding repartition versus coalesce and avoiding the small files problem. Fourth, avoid unnecessary computation by caching only reused datasets, selecting the correct persistence level, and preferring built-in Spark functions over Python's UDF. And most importantly, do not apply these techniques blindly. Use the Spark UI and the execution plan to identify the actual bottlenecks first. Because Spark optimization is not about memorizing random settings. It is about reducing data read, data movement, uneven work, and repeated computation. That is the structured answer an interviewer is looking for. Comment Spark if you want a separate video explaining how to read the Spark UI. If this video helped, drop a like and subscribe to Big Data Factory. This is all for today. I will see you in the next video. Till then, keep learning and keep building. Bye bye.